Good morning, everybody. I'm Bob Jaffe, sort of, as my department head said earlier this morning. I'm not quite sure what that means. I'd like to say, first of all, it's a real pleasure to be here. I've been here 92% of the time of the existence of the CTP. So, Krishna, I've got you there. Our first speaker really needs no introduction, so I'll be very brief. He's the Hermann Feshbach Professor at MIT since the year 2000. Frank Wilczek is well known to you for his work on asymptotic freedom, of course, but many, many other fields, axions, solitons, the condensed matter of QCD, and on it goes. Today he's going to talk about the symmetries of time. Frank.
Ordinary people, insofar as they think of time at all, think of it as kind of a background in which they're immersed. And philosophers have all kinds of confusing things to say about time. But physicists think of time as a thing with properties of its own. And in particular, some of the most profound properties are its symmetry. And much of my career has been connected in one way or another with problems concerning the symmetries of time. And in ruminating back on a 50-year time scale, that seemed like an appropriate theme. So I'll talk about the symmetries of time as they relate to the past, as they relate to current frontiers of physics, and even, I think, future frontiers. So the first symmetry of time I'd like to talk about is time reversal symmetry, also called T. To me, the main theme of time reversal symmetry is that it gives you the road to axions. So few aspects of experience are as striking as the asymmetry between past and future. We remember the past, we plan for the future, we remember being young, we look forward or not to getting old, and so on. And if you run a movie of everyday life backwards, it does not look like everyday life. Here's a picture, not quite everyday life, but something that you'll recognize. And you'd be very surprised if you saw that happen. Okay, you'd find that you'd have seen a lot of dust collected on the ground for no particular reason, then it starts shaking, then it flies up into the air, reassembles, and you say, where is all that kinetic energy going to go? Well, it goes into potential energy as the atoms recombine into the explosives. The remarkable thing is, although you would never see such a thing in everyday life, or even if you went to see buildings being taken down, nothing in that picture, in that movie, would disobey the laws of physics. If you went down to the level of atoms and their reactions and fundamental things going on, all the equations of physics would basically be satisfied. So it's by no means necessary for constructing a description of experience that the equations should be symmetric between past and future. In fact, it's kind of an embarrassment. There's a whole subfield of physics apologizing for the fact that the equations are too symmetric, and you have to spoil that to get macroscopic irreversibility of time. Because time reversal symmetry, T, was a notable property of fundamental physics for several centuries, starting with Newtonian mechanics, surviving through general relativity, through the mature understanding of electrodynamics, the quantum theory, and so forth. Why? It makes trouble. It doesn't help us describe the world. In fact, it makes it harder, as I said. So as long as T symmetry appeared to be an exact fundamental feature of physical law, it was unclear that asking why would be fruitful. If you've ever interacted with a small child, you know that it's always possible to keep asking why. And say, why is the sky blue? Well, it has to do with how the light is scattered. Why? Well, because there are these atoms and they oscillate. Why? Well, there are these strings. And at some point, you just have to say, that's it. That's just the way it is. You hit rock bottom. And while T-symmetry appeared to be an exact feature of the fundamental laws, you could have taken the attitude that that was rock bottom. It's a nice principle you can enunciate. It's pretty, it's symmetric. What more could you ask? However, it turns out to be also false. In 1964, James Cronin and Val Fitch, and two other guys who never get mentioned, discovered a subtle effect in K-meson decays that slightly violates T-symmetry. Now, actually, it's CP symmetry, but we believe that CPT is a very good law of nature, so T asymmetry is implicated in CP asymmetry. And since then, T-symmetry has also been seen to be violated directly. So T-symmetry is definitely not rock bottom. It's something we need to explain, why it appears so good, but yet not exact. Why? And the wonderful thing is, we've almost nailed it. Thanks especially to the work of Kobayashi and Masukawa, plus everything that goes into this modern physics and the standard model, we've learned that the basic sacred asterisk principles of modern physics, that is relativity plus quantum mechanics plus local symmetry, are extremely powerful. If you try to make theories that are consistent with those principles, it's very, very constraining as to the possibilities for consistent interactions. And when you apply this to the question of T-symmetry, so you impose those laws, you find as an indirect, almost accidental consequence that if there are three families of quarks and leptons, as observed in the world, there are exactly two possible sources of T-symmetry violation that are consistent with the general principles. This was the wonderful work of Kobayashi and Masukawa, which in fact predicted the existence of the third generation of quarks and leptons. One of those beautifully explains what Cronin and Fitch observed, and a lot more. Technically, it's a complex phase in weak mixing angles, and leads to a rich theory of CP violation in a wide variety of processes, now involving heavy quarks and the original phenomena. The other doesn't happen. So at the end, we're still left with why. The story is not quite finished. So over the past 40-plus years, there have been several attempts to explain it, but only one has stood the test of time. Little joke there. Yeah. This is that we promote the unwanted term. So there's a number that appears in the fundamental description, in the Lagrangian. You promote that number to a field, so it can depend on space and time. If it's a dynamical entity, if it's a field, it obeys dynamical equations, it can evolve, and so you can have a theory of evolution that tells you why this goes to zero. And of course, you need a particular theory, but it can be done in a very elegant way with symmetry in a way that was first set up by Roberto Peccei and Helen Quinn. It's called the Peccei-Quinn symmetry and the Peccei-Quinn mechanism. So the new field is made out of a new kind of particle, okay, in quantum field theory with these sacred star principles. By the way, sacred star means nothing is sacred, really, but it just means that if one of those principles, relativity, quantum mechanics, locality, were observed to be violated, we'd really have to unlearn a lot of things we already think we understand, and it would be, we'd rather tinker around the edges unless we're really desperate. Okay, so the new field is made out of a new kind of particle that comes out of the principles of quantum field theory. And Pecci and Quinn didn't notice that there was such a particle, even though it's the most important consequence of their theory, so I got to name it. And I named it the Axion in homage to a laundry detergent. It's a true story. Here's the proof. I was very young in those days, and just had as a fresh memory my expeditions with my mother to the grocery store to buy things. Having seen this detergent on the racks, I thought, gosh, that sounds like a name of a particle. It's nice and Greek and short, and if I ever got the chance to name a particle, I'd use it, and I did. And I told the editors of Physical Review Letters that it was because this particle cleaned up a problem with an axial current. Kind of an in-joke, but it got past that rather conservative body of people who protect physics from stupid names. So, so do axions exist? Well, we still don't know for sure, but in recent years, the stakes have risen dramatically. We can calculate that axions get produced in the Big Bang and survive to this day. The relic axion gas has properties consistent with the observed properties of the astronomer's dark matter. You will probably hear quite a bit more as the day goes on about the dark matter, so I'll be very, very schematic here just to mention that there are several different ways of determining that there's more mass out there in the universe than is in forms that our telescopes and other kinds of receivers are capable of seeing signals from. And so there's some kind of mass that looks like some kind of particle. We don't know what it is, but it's been seen in many different contexts, so-called cold dark matter. So that was galactic rotation curves. This is gravitational lensing, where something is lensing, but there's nothing there. So what's causing some invisible mass is causing the deflection of light. So the bottom line, after a lengthy analysis, putting together axions and cosmology, is that if axions exist at all, they must contribute significantly to the dark matter. Coincidence? I'd like to think not. Many of us think not. So plausibly, the axions dominate it. Several clever strategies for axion detection have emerged. They are very, very feebly interacting particles, I should say, because of the tasks we ask them to do within the theory. They have a very specific identity. We can say a lot about their properties. The only thing we don't know is one important number, its mass, which is also tied up to the strength of its interactions. So because we can make such a tight theory, we'll know axions if we see them, and we can design experiments to go out and detect them. So it won't be easy. The theory tells us that these guys indeed interact extremely weakly with ordinary matter. So sort of reminiscent of neutrinos or gravitational waves or Higgs particles, things that may be very, very difficult and you need patience, but we know what we're looking for. And there are determined people now all over the world searching for axions. This is one representative group in one representative institute, the Center for Axion and Precision Physics in Korea. And you can see how determined they are. And, so let's hope that John Bolton gets contained and we don't. This is the strategy of the search. Axions are out there, but they interact very weakly with ordinary matter, but in ways we can predict. And we can predict, for instance, that in the presence of a strong magnetic field, axions can convert into ordinary photons, and then with suitable eyes, you can detect the photons. Another strategy that's very beautiful and has been pioneered at MIT is called the abracadabra experiment. It's basically you set up a magnetic field, a time-dependent axion field in the presence of a magnetic field sets up an effective current, and that current then generates other magnetic fields that are time-dependent. You can measure. It's all very pretty and beautiful electrodynamics, axion electrodynamics, and that's another strategy that's being prototyped now and scaled up to detect the axion background. Finally, I'll just mention, because it's really fun, that axions could also form atmospheres around black holes. And it's not true that black holes have no hair. It's just their hair is not very visible. It's an axion cloud that surrounds the black holes. And it does affect their gravitational wave signals when the black holes collide or do things. Also causes rapidly spinning black holes to spin down. So when we learn more about black holes, we can find out if they have these kinds of axions, atmospheres. So a specter is haunting physics, the specter of axions. It's out there, maybe the dark matter. But I don't want to leave you with that image. Really, it's a matter of doing a beautiful thing, of keeping the past and the future in balance. Okay, so much for time reversal symmetry. Now I'd like to talk about another profound symmetry of time called time translation symmetry. And to me, the importance of time translation symmetry is that it's the road to time crystals. So time translation symmetry may be the most fundamental symmetry of all, in all of physics, because, well, although strangely enough, it doesn't seem to have a less than 7-syllable name, time translation symmetry. I'll call it tau for present purposes. Tau is the principle that instructs us that we can discover eternal laws. That's how fundamental it is. It tells you that if you translate time by a certain amount, you still have the same laws. That's another way of stating it, that profound principle in terms of a symmetry. Tau is connected through Noether's theorem to the conservation of energy. Also, quite a profound principle of physics, as Professors Jaffe and Taylor will tell you. So, spontaneous breaking of spatial translation symmetry is commonplace. Indeed, most common materials like to form crystals at low temperatures and do so spontaneously, as long as you keep them quiet so they can do their thing without disturbing them or shaking them up. So physicists are accustomed to making analogies and connections between space and time. Therefore, it's natural to ask whether there are states of matter that correspond to crystals in time, as opposed to crystals in space, thus time crystals. This was, despite how natural it is, this was somewhat of a heretical notion when I proposed it in 2012, and I took a lot of grief over it. But, well, here's the concept. And a beating heart is a sort of time crystal, but it's not very precise. It requires feeding and maintenance, and it's complicated. The notion of spontaneous symmetry breaking can be made precise, but basically it's something, it can be made mathematical and precise. I won't do that here, but it's basically a legitimate time crystal as opposed to a beating heart is something that does better on all these axes. So then there was a question, can tau be broken spontaneously? This was controversial and is conceptually subtle, because usually when we ask what do things like to do, they like to settle down into the state of lowest energy. But if you're talking about time translation symmetry, when you break time translation symmetry, energy is no longer conserved. So you need other criteria. It becomes a much more subtle and interesting business. So the answer, however, now is yes, it can be broken spontaneously. And this was first announced less than 2 years ago. Physicists just created the world's first time crystal, and this was a complete lie. The subscript is a lie, the subtitle is a lie. These things actually exist, at least if these things refer to the picture. The picture has nothing to do with the actual experiment, but and then in March, the March 9th edition of Time Crystal had another lying picture of what a time crystal looks like on the cover, but this was a banner issue of Nature in which they had a news feature, a news and views, and 2 experimental papers that announced the discovery of time crystals. Now, it's a little bit too technical subject to enter into here, but for a physicist, maybe the most defining feature of a new state of matter is that you have a phase diagram and transitions into and out of the state. And here it is for time crystals as a function of an interaction parameter and a disorder parameter. You get different states where you have breaking of time translation symmetry or other kinds of well-understood states that your system, this is a system of spins, interacting spins can exist in. 5 minutes, okay. So the big picture is that the study of tau breaking is revealing shortcomings in the hitherto conventional view of equilibrium, which would say that things spontaneously devolve into just one static state as you take them into equilibrium at some definite temperature, including 0. Notably including the emergence of robust, self-organized quantum structures in noisy, randomized systems. That's what these time crystals are, or the experimental ones. Now, usually, the road to commercialization of a product is slow and arduous, typically takes 10 to 15 years, but in the case of time crystals, it was actually acausal. And you can find time crystals on the internet, and they've been used for very advanced purposes by Doctor Who. So finally, in the very, very little time I have left, if any, 3 minutes? Okay. Well, God did a lot in the first 3 minutes. So I'll discuss something that I'm working on now and haven't written down very much, but we're preparing it. Something I call TEMI. I like to name things, axions, anyons, time crystals, and familons, others. This one is another thing I really want to introduce into the physics literature, because if you make a cyclic permutation of these letters, then you get a word each time. And as far as I know, that's the only 4-letter combination that has that property. So we really need to have that. So the idea is mixing past and future. So we generally regard the equations of physics as a recipe for evolving states from the past into the future. And I'll write it this way for a reason you'll see momentarily. So you have your initial state, and I'll just put it in an abstract quantum mechanical form. You have a unitary evolution that which the laws determine what that matrix ABCD is, takes initial states into final states. And our laws of physics tell us about that matrix. Formally, we can also invert that relation to infer the past from the future. So, in order to treat not only the laws symmetrically, but also the conditions symmetrically, it's natural to think about mixed conditions, where you have some conditions fixed in the past and some fixed in the future. Can you get a well-defined problem by doing that? Well, yes, you can. As long as that corner matrix D is invertible, you get a unique solution. And since determinant D equals 0 requires 2 real numbers Generically, it's to vanish. Generically, it's not zero. And even as a function of time, it's never zero. So this line of thought, setting up symmetric boundary conditions or boundary conditions that have two kinds of worlds that evolve in different directions of time, can lead us into many interesting adventures. We can think about time-symmetric Big Bang cosmology, where one form of matter goes this way from future to past, our future to our past, or another form goes in the way we know about. We can have warring thermodynamic arrows coming from, if the laws of thermodynamics ultimately have a cosmological origin, which I think most of us believe, this will have warring thermodynamic arrows coexisting, and open up free will, a discussion of free will and paradoxes of causal loops that arise at the macroscopic level on a sound microscopic basis, so we can really be forced to face up to them rigorously. So it's going to be fun, and I'll close by making one final prediction that only apparently violates the second law of thermodynamics, which is that as time goes forward, our ideas about time will get clearer. Okay, thank you very much.
So we have time for some questions.
Yeah, should have stayed wired up. Okay.
Time reversal symmetry seems to be superficially at odds with the time translations invariance.
Oh, no.
I mean, you were just saying you're going to evolve the equations back and forth sort of simultaneously, but
Okay, so time translation symmetry, time reversal symmetry has to do with the laws of physics. It's a much more radical and unexplored, or less explored idea to have the states have non-trivial properties under time reversal. That's the TEMI idea. And time translation symmetry is a separate idea that has to do with the homogeneity of time, not the direction. So it's certainly consistent with time reversal symmetry, but it's neither implied nor.
symmetry in the direction of time, you can still run the evolution to these two different types to the states in the past and the future.
Well, if you violated time translation symmetry, you'd have to be quite artful about it in order not to violate time reversal symmetry. That's true, yes. Yes.
Could you clarify again why the time crystals are or are not periodic? I would think periodicity would be a crystal in time, right?
They are periodic.
Oh, I didn't understand that from your picture.
No, they are, but in,
The diagram shows periodicities.
excuse me?
The phase diagram showed periodicities.
Oh, no, the phase diagram was not a picture of dynamical variables. It was a picture of states of matter. So a phase diagram in the sense of thermodynamics, showing you different phases that this physical system could be in, depending on the relative values of different elements.
So the periodicity changes.
No, actually, in this particular thing, the periodicity doesn't change. But it's either periodic or not, depending on whether you're in the time crystal phase or not.
So you mentioned beating hearts, I would say engines in general.
Clocks.
Clocks.
Yes.
So these are irreversible things, right?
That's right. They need care and feeding. They run down. They're not closed systems.
And you can get work out of them. So
Yes,
a time crystal,
you can.
you cannot get any work out of them.
No, no. We don't. We haven't figured that one out yet, and probably never will. What?
It's kind of necessary, right? Because otherwise it would be an engine rather than
Yes. Right. Although, just like the sacred star principle, it's ultimately empirical whether you can do these things.
Way up in the back.
God hasn't said that there's no second, that that the second law of thermodynamics is true, and even if he or she did, I wouldn't believe it.
I can close the something to you. Hi, thank you
Yes.
for the talk. I'm a member of the Live Collaboration, so indeed we are looking for axion clouds around the codes.
Yes.
However, as far as I understand, it's probably going to take the next generation of ground-based detectors, given the expected strain. So I wanted to ask you, what are the possible timelines for other lines of discovery of axion? Whatever times being for the stage.
Well, we don't really know. It depends very much on what the properties are, and a number of these experiments are still at the prototype level, need to be scaled up. But they are maturing, so you can't wait, you can't dawdle forever. You guys better get to work. Yeah.
2030s.
What's that?
From our side, it's going to be 2030s, probably.
2030s.
Comes after likely.
Oh, in the 2030s?
Yeah.
Okay. So I'll keep taking my vitamins.
So we have time for one last question.
One question is, what happens actually to entropy? Can it still define in the meaning?
In which context?
Sorry, when
Time crystals?
no, and
Oh, in tennies? Well, entropy always involves some kind of, you can still define useful concepts of entropy. If you want, the most interesting thing probably is that you have these time-symmetric things with two different kinds of matter that interact weakly and have a different thermodynamic arrow of time. So there would be an entropy for one, an entropy for the other. They would evolve in different directions, increase in the two different directions. And then exactly what happens, the details of how they exchange, that's under study.
So let's thank Frank for his exciting talk.